This is the first video on section 6.4, gradients and directional derivatives. So first, I'm going to look at definition 175, notation 176, and definition 178, sort of all at once. And so we're looking at the gradient of f, both at a point and the gradient of f as a function. And so we start with a function of n variables, f, and then we have c in Rn, and we're assuming that all the first order partial derivatives of f exist at c, and so we look at those partial derivatives. So we have the partial derivative of f with respect to the first variable, the partial derivative of f with respect to the second variable, and so on down to the nth variable, and we substitute c into each of those partial derivatives, and that's a vector. That's a vector in v sub n. So that's an n-dimensional vector. That's the gradient of f at c. And then we can look at the gradient of f as simply a function from Rn into Vn, where we calculate the partial derivatives, and then we can substitute a variable in, assuming that the partial derivatives exist at these variables. And so now we'll look at example 177. So we're given a function of three variables. It's a polynomial of three variables. So we have x squared y plus xz plus y cubed. And we're going to calculate the gradient of f at the point 1, negative 2, 0. So we calculate each of the first order partial derivatives, f sub x, f sub y, f sub z. And then we simply substitute negative 1, 2, 0 in for each of these. So we calculate the partial derivative with respect to x at the point 1, negative 2, 0, and we have negative 4. We substitute 1, negative 2, 0 into the partial derivative with respect to y, and we have 13. And then finally we look at the partial derivative with respect to z, substitute 1, negative 2, 0, and we have 1. And so the gradient of f at the point 1, negative 2, 0 is equal to the vector negative 4, 13, 1.